Hi, this is the TheoryStation. The program is Principles of Math, and this series is the Basic Ideas series. This is the second installment. So right now I just want to start giving some ideas about that formal analysis arrow. These are things that you've probably seen a little bit of or heard of, and it's not going to be very deep or challenging, but just to get us warmed up. So what I want to start talking about is one of the most basic sets of tools that we have, which is logic. Logic, roughly, what it does is it gives us a way of going from a set of sentences and inferring new sentences from those. Now, the sentences we're talking about they're not subjective statements. They're sentences that are either true or false, but they're not both true and false, of course. So, for example, 2 plus 3 equals 5 is a true sentence. 2 plus 7 equals 24 is a false sentence. Those would both be the kinds of sentences that we're talking about. So in logic, we don't want to write out sentences like that all the time, and we want to be very general. So we have this notation. I'll use lowercase letters like P or Q or R, and those will just stand for these sentences. They're either true or false, but not both. Okay, so with that notation, the first thing I want to do is point out that from these simple sentences, we can build up more complex or compound sentences. One of the simplest things to do is to start with the sentence P, and then say that sentence is false. The notation we use for that is this kind of funny bracket symbol next to the P, and we read this as not P. We're saying that P is false. So that's one easy way of getting a new sentence from P. Suppose we have two sentences, P and Q, and we want to say that they're both true. Well, there's notation for that again. It's this kind of wedge shape. We put that between them, and this is saying that P and Q are both true. This is the compound sentence P and Q. This is called conjunction. The term that's used is it's an operator because it's operating on two different sentences to give us a new sentence. We can also do ors, and for that we're just going to flip that wedge upside down. This is the sentence P or Q. What that means is that at least one of P or Q is true. And they might actually both be true. We're just saying at least one of them is true. So I should point out, this is called disjunction. And I should point out that there's a couple different ways we use disjunctions. This way is the inclusive way because we are allowing for the possibility that both sentences are true. So there's also an exclusive use of or. So if you tell your kids you can have cookies or ice cream, you're giving them a choice of one, but not both. That's an exclusive use. In logic, though, we use it inclusively. So enough said on that. Another thing we can do, if we have two sentences, we can say that one implies the other. So here we're saying that P implies Q, what that really means is that if P is true, then Q has to be true as well. We're asserting this. This is called logical conditional, and I should point out there is a little bit of ambiguity there because what if P is false? What does this conditional statement mean? Well, in ordinary language, we don't really have a set rule for that, but in logic, we have to make sure that these are completely precise. And so we just adopt the convention that if P is false, then the conditional statement is true. It's not true in an interesting way. We say it's true vacuously. And there's not, if that seems weird to you, there's nothing that that does not lead to any sort of weird consequences. It's just a convention that we use to make that statement precise. And then the last one I'll do is the biconditional, which is basically the P implies Q going in both directions. So the way we say that is P if and only if Q and that just means that either P and Q are both true or they're both false. They have the same truth value. That's the term we use for whether a sentence is true or false. Okay, so those are the main ways of building up compound sentences from simple ones. And we can be a little bit more precise about what these mean, but I think that gives enough of an idea right now. So let me talk a little bit about logical proof now. There are, well, just to give the general idea of what a logical proof is, we have some, well, I think of it as climbing a ladder in a way. So here's a ladder. And here are the rungs of the ladder. And we're here. We get to start partway up the ladder. The step that we're on and the steps below are the assumptions that we have in the proof. Okay. Now, eventually we need to get up to this top rung. There's something that we want to prove. And what we're going to do is, from these assumptions that we have, these sentences that we're starting with, we apply our logic. There's going to be logical rules of proof that that allow us to take a step up the ladder. Okay. Now, the virtue of these rules of proof is that it's sort of like, when you climb a ladder, if you make sure that you have two hands on the ladder and one foot on a rung at all times, so when you take that next step up, you're still secured to the ladder. There's no way you're going to fall off. Okay. So these logical rules are going to allow us to take that step up the ladder with no chance of falling off because we're holding onto the ladder with two hands and we have one foot on a rung. And then we just keep applying those rules and we get another sentence and another sentence. And eventually we climb up the ladder. At each step of the ladder, we're secured to the ladder because we're applying these rules of proof. There's no chance we're going to fall. And eventually, if you are doing the proof correctly, you get to that last step that you wanted. The virtue of this is that you can climb a very, very high ladder, and if you just are always applying these rules of proof, There will never be a chance of falling off, okay? So to put a little more detail into this, what are the rules of proof that we're talking about? So I'll give you one. It's called disjunctive syllogism. So disjunctive syllogism says, suppose you have a disjunctive statement, P or Q. So think of that as being the first rung on the ladder. It says at least one of those two sentences is true. But now suppose the second rung of the ladder is not P. And that's where we're standing, okay? Well, this logical rule of disjunctive syllogism allows us to take another step up the ladder and conclude that Q is true. And that makes sense, right? If at least one of them is true, but if at least one of them is true, but P is not, then Q must be. That is taking a step up the ladder. Another well-known rule is modus ponens, which says, suppose you have a conditional statement, P implies Q, and you also know that P is true. Again, think of those as the first two rungs of the ladder, and that's where we're standing. This should be pretty intuitive, but modus ponens allows us to conclude that Q is true, right? The conditional statement tells us that P implies Q, and if we also know P, well, Q follows. That's taking a step up the ladder. Just one more. Modus tollens is a related idea. Again, we're starting with a conditional statement, P implies Q, but now instead of P, suppose that we know Q is false. Well, from those two things, it should be pretty clear. If P implies Q, but Q does not hold, P can't be true. So we can conclude not P. So again, that's just taking a step up the ladder. So this is kind of how logical rules of proof work. There are some other ideas in logic. Let me just give two of them, and then I'll end this installment. So one is the idea of a conditional proof. So here, imagine that you're in an argument and you want to show that P implies Q. So you're somewhere up the ladder, and the next, you want to get to this P implies Q rung. So how do we show an implication like that? Well, what we do is we suppose, actually I'm going to write that differently. We suppose P is true, and then we see if we can apply our rules of inference to then get to Q, right? We take P on as an assumed premise, and then we try to deduce Q from that. If we can do that, that means that actually Q does follow from P, and we've shown the implication that we wanted. Here's one more that you probably have heard of, and in my experience, it kind of throws students off a little bit, but it's really not that strange or hard, but it's called proof by contradiction, or reductio ad absurdum. Okay, so here's a case where we want to show some sentence. Let's call it P. So what we're going to do then is, let's suppose not P. It's kind of weird, right? If you want to show P, what you do is you suppose not P, and then apply the rules of proof, and suppose that we can show a sentence. We can, by applying these rules of inference, we can show a sentence of the form Q and not Q. Well, that's a contradiction, right? At the very beginning, we said these sentences are true or false, but they cannot be both true and false. So this can't happen. So what that means is that our supposition must have been incorrect. It can't be that P is false. So we've shown that P is true. Another way of thinking about this is, there's two possibilities. Either P is true or it's false. Okay? We want to show that it's true. What a proof by contradiction does is it shows that this right branch, where P is false, can't happen. Okay? It's really just proof by elimination. We do this all the time, right? We deduce things by elimination, and that's all proof by contradiction is. Okay, so it's not really that mysterious. All right, so this is just a very, small taste of what logic is like and what it does for us, but it allows us to climb this ladder of deduction to get these conclusions that follow from our assumptions, and it's an important part of that formal analysis arrow. And I think that's enough on logic, and we'll wrap up this installment.